Uh, okay, so last time we talked about the minimum variance unbiased estimation, and one of the things that we talk about is the sufficient statistics. So a trivial example is to calculate the sample mean. So when we are calculating the sample mean, we already know that the sample mean is a good estimator for the mean. So um, we collect a set of data. For example, this S1 is a complete set of data. The S1 is a complete set of data. This S1 is a complete set of data. So when we are asking the questions about whether or not it's sufficient, then the S1 is definitely sufficient. The S1 is definitely sufficient. Then how about S2? We mentioned about that if you have S2 with respect to the sample mean, then of course it's definitely sufficient because you can take that X2 and then still take the average and you can still create this estimator. So it's definitely sufficient. Then how about S3? S3 is sufficient because if you know it, then you can still divide S3 by its mean, by its set number of samples. So you still come up with the unbiased estimator. So that is we will say that those things are sufficient. Those things are sufficient. Okay, so uh, the next thing is we need to know if it's minimum sufficient. Minimum sufficient meaning that it has the least number of data and yet still sufficient. So if we look at the three statistics, we will find that S3 is the minimum and yet is still sufficient. So that will be the minimum sufficient statistic. Minimum sufficient statistic. Okay. So the next thing is let's try to look at the PDF. Let's try to look at the PDF. As you know, this PDF, when it is treated as a function of the theta, then it will be a likelihood function. So we would like to know if the PDF can be factorized, into a function of the minimum sufficient statistic. And of course, in this case, it will be yes. The answer is yes. So T of x is equal to summation of xn equal to 0. Then the knowledge of the value of this statistic will change the PDF to the conditional probability density function. So once those sufficient statistics given, then PDF is completely described. Therefore, we will say that the statistic is sufficient. Okay, so if the statistic, let's look at this. If the statistic is sufficient for the estimation of A, this conditional PDF should not depend on A. Should not depend on A. If it did, then we could infer some additional information about A from the data, in addition to that already provided by the statistic. So let's try to look at an example. If your PDF, when T0 is given, still depends on A, then what that means is you have additional information, right? You have additional information, meaning that this T0 doesn't completely and sufficiently describe all the information about A. That's why it depends on A. Therefore, this T0 is not a sufficient statistic. Then the other case is, if we try to look at this case, while T0 is given, then the PDF is completely described and it doesn't depend on A. Therefore, no additional information can be provided after T0 is provided. Therefore, this T of X is sufficient. So that's the meaning of sufficient statistic. If we just try to look at this in a more verbal and oral, understandable way, we will say that sufficient statistic provides sufficient information about a specific parameter. In this case, that will be A. But if a sufficient statistic provides information about A, it may not be sufficient for B. It may not be sufficient for another parameter, let's say C. So let's be clear, a sufficient statistic, while it's described as sufficient, it is sufficient with respect to a specific parameter A. Okay, it's not like general. It's not general. It has to be specific. Okay, so let's take a look at this example 5.1. Verification of a sufficient statistic. Let's consider the PDF of 5.1. To prove that this is a sufficient statistic. This is a sufficient statistic. This is a sufficient statistic. We need to determine this does not depend on A. So by the definition of the PDF, let's write it out. And this is Bayes' rule. When you have a probability density function of X conditioned on the two parameters, it can be written in this way by using Bayes' rule, 贝氏定理. So if you review the Bayes' rule, you will find that this is identity, a probabilistic identity. So note that P of X is functionally dependent on X, so that the joint PDF P of X is equal to this text on non-zero values only when X satisfies this. So the joint PDF is there for this. So we can rewrite this in this way, which means that this term is written into this form. Okay. So now let's turn to the next page. That is this. So page 104. So clearly P of X is distributed by this. For this distribution, I think we done it before. We have done it before. So it's a summation of n. Recall that it's a summation of n Gaussian random variables. So when you sum it up, it gives you n h and then n sigma square. So this can be written into this form. Let's see this. What is this? This is in fact a Gaussian distribution, right? It's a Gaussian distribution with n Gaussian random variables. So you have this exponent n divided by 2 and exponent for the summation. And then you expand this term, it gives you this second order term, x squared minus 2at plus na squared. Okay, so let's go one step further. We get this t equal to t0 because if it's not equal to T0, then all this PDF is in fact equal to zero probability density, except T of X equal to T0. Okay, so and then this term will become this, because if you try to write this term, write it out of the exponent into this term, exponent, and the remaining terms goes to here. So you get the numerator, term, and the denominator term is like this. Let's recall the denominator. The denominator term is this term. So you have this as the denominator, and then what? Then if you try to look, you actually have some common terms here. 2 pi sigma square. Those common terms subtracted out, and then n square root of n goes here, and then you have this t0, and it subtracts with this one, so it goes out. This cancels this. Some of the terms in this is cancelled by that, so it remains. The remaining term is over here. And then what next is this term goes here. So let's try to look one more time. You have P of X condition on T0 and A, which is eventually equals this term. This term is all known variables. Everything is known, so it doesn't matter. And then you have summation of x squared, and then exponent of this. So this does not depend on A, right? So eventually, what we know about this is once we have information about summation xn, then it will be sufficient for A. Okay, so that is the example. Then of course, let's take one step back and see. It's to calculate the mean of this is so-called the DC label problem, right? DC label in a Gaussian random noise. So that would be an example. And then to find the sufficient statistic, there is this theorem 5.1. If we can factor the PDF in this form, let's take a detailed look at this form. PDF is equal to G T of X theta H of X, meaning that you have a function of sufficient statistic, and then the parameter only multiply with the function of theta. So what that means is your theta, which is the unknown parameter, cannot be mixed with the theta x. It can only interact with the theta x through the sufficient statistic T of x. Okay, that's the requirement. It cannot be in a mixture with the data. It has to be in a mixture with the data through the form of T of x. That will be the requirement for the Fisher factorization. Okay, so G is a function depending on x only through T of x, and H is a function depending on only on x. Then P of x is a sufficient statistic for theta. Conversely, if P of x is a sufficient statistic, then the PDF can be factored in this form. So let's take a look one more time. If theta has to interact with x, it has to be through this T of x. In the other aspect is, if you take a look at this x, h of x, there is no theta, which is the unknown parameter in h. So what that means is the PDF is separated. The PDF separates the data and the unknown parameter. It's separated. They don't interact with each other in the PDF. Then we will say that P of x is a sufficient statistic. So there is no x in this G. The only thing in G is the T of x. And there is no theta in H. It cannot be. If there is a theta in H, then it will not be a sufficient statistic. Okay, so then we have complete the Fisher factorization theorem, the Fisher factorization theorem. So now we re-examine the problem discussed in this session. There the PDF was given, where we know that sigma square is assumed known. To demonstrate that the factorization exists, notice this sentence. If P of x is a sufficient statistic, then the factorization will sustain. If the factorization sustains, then T of x is a sufficient statistic. So the description is the two-way description, sufficient and necessary condition. Okay, so we want to double check about this DC label in WGN. So let's write out the PDF of the DC label problem. So there is a term summation xn minus a squared equal to this. This is just a second order polynomial, and you expand the polynomial, so you get this. So the PDF is factorable as this one. Okay, let's take a look. You have P of x a equal to, this is Gaussian. This is Gaussian. Then exponent this whole business, right? This whole equation. Then you put it into two forms. The other one of the form is the x squared that goes here, and x with NA squared that goes here. So now let's check carefully. We see that this is just a, it's a constant. It doesn't matter. This is a constant. This is T of x, where T of x is what? T of x is defined this way. So you see T of x in, do you see T of x in G? I think if you check carefully, you see, you see that T of x is actually over here, right? See my cursor? T of x is over here. So this is T of x. So if you write this whole thing as G T of x, you see T of x over here. And be aware that other than T of x, there are no other terms with x. You see, there is no x here. There is no x here. There is no x here. The only x that exists is in T of x. So this is what we call by G of T of x a. And then the rest is put into h of x. So we will be able to create this P of xa into this G of P of xa and H of x. So clearly then P of x is a sufficient statistic for A. Notice that P prime of x is 2 times the original P of x is also a sufficient statistic for A. And in fact, any one-to-one function of this is a sufficient statistic. So the sufficient statistics are unique only to one-to-one transformations. In other words, if you have 2 multiplied by this is still a sufficient statistic. You like to divide by 2, you want to multiply by 3 to 4, whatever you want to do with a sufficient statistic, as long as it's a one-to-one function of sufficient statistic, it is a sufficient statistic. Okay, so I think we use this DC table as a very good example because it's easy, it's simple, its formula is understandable and not that complicated. So we see it clearly particular for this format. It shows very clear factorization within this form. If you see it carefully, this is in fact a very good correspondence of this term and this term. Okay, so I think this is the end for session 1.